Hello, welcome to IT Expert YouTube video series. Today we are going to talk about difference between Hadoop and Spark. What is Hadoop? First released in 2006, Hadoop was created by software engineers Doug Cutting and Mike Caffarella to process large amounts of data. Initially using its namesake file system and MapReduce, a programming model and processing engine that Google promoted in a 2004 technical paper. Hadoop provides a way to efficiently break up large data processing problems across different computers, run computations locally and then combine the results. The framework's distributed processing architecture makes it easy to build big data applications for clusters containing hundreds or thousands of commodity servers, called nodes. The main components of Hadoop include the following technologies. HDFS. Initially modeled on a file system developed by Google, HDFS manages the process of distributing, storing and accessing data across many separate servers. It can handle both structured and unstructured data, which makes it a suitable choice for building out a data lake. YARN. Short for Yet Another Resource Negotiator but typically referred to by its acronym, YARN is Hadoop's cluster resource manager, responsible for executing distributed workloads. It schedules processing jobs and allocates compute resources such as CPU and memory to applications. YARN took over those tasks from the Hadoop implementation of MapReduce when it was added as part of Hadoop 2.0 in 2013. Hadoop MapReduce. While its role was reduced by YARN, MapReduce is still the built-in processing engine used to run large-scale batch applications in many Hadoop clusters. It orchestrates the process of splitting large computations into smaller ones that can be spread out across different cluster nodes and then runs the various processing jobs. Hadoop Common. This is a set of underlying utilities and libraries used by Hadoop's other components. What is Spark? Spark was initially developed by Matej Zahariya in 2009, while he was a graduate student at the University of California, Berkeley. His main innovation with the technology was to improve how data is organized to scale in-memory processing across distributed cluster nodes more efficiently. Like Hadoop, Spark can process vast amounts of data by splitting up workloads on different nodes, but it typically does so much faster. This enables it to handle use cases that Hadoop cannot with MapReduce, making Spark more of a general-purpose processing engine. The following technologies are among Spark's key components. Spark Core. This is the underlying execution engine that provides job scheduling and coordinates basic input or output operations, using Spark's basic API. Spark SQL. The Spark SQL module enables users to do optimized processing of structured data by directly running SQL queries or using Spark's Dataset API to access the SQL execution engine. Spark Streaming and Structured Streaming. These modules add stream processing capabilities. Spark Streaming takes data from different streaming sources, including HDFS, Kafka and Kinesis, and divides it into micro batches to represent a continuous stream. Structured streaming is a newer approach built on Spark SQL that is designed to reduce latency and simplify programming. mlib. A built-in machine learning library, mlib includes a set of machine learning algorithms, plus tools for feature selection and building machine learning pipelines. What are the key differences between Hadoop and Spark? Hadoop's use of MapReduce is a notable distinction between the two frameworks. HDFS was tied to it in the first versions of Hadoop, while Spark was created specifically to replace MapReduce. Even though Hadoop no longer depends exclusively on MapReduce for data processing, there is still a strong association between them. In the minds of many, Hadoop is synonymous with Hadoop MapReduce, said Eric Fesser, director and chief architect at consulting firm Deloitte. MapReduce in Hadoop has advantages when it comes to keeping costs down for large processing jobs that can tolerate some delays. Spark, on the other hand, has a clear advantage over MapReduce in delivering timely analytics insights because it's designed to process data mostly in memory. Hadoop came first and revolutionized the way people thought about scaling data workloads. It made big data environments with large volumes and varying types of data feasible in organizations, particularly for aggregating and storing data sets to support analytics applications. Consequently, it is often adopted as a platform for data lakes that commonly store both raw data and prepared data sets for analytics uses. While Hadoop can now be used for more than batch processing, it is primarily suited to analysis of historical data. Spark was designed from the ground up to optimize high-throughput data processing jobs. As a result, it is suitable for various uses. Spark is used in online applications and interactive data analysis, as well as extract, transform and load ETL operations and other batch processes. It can run by itself for data analysis or as part of a data processing pipeline. Spark can also be used as a staging tier on top of a Hadoop cluster for ETL and exploratory data analysis. That highlights another key difference between the two frameworks. Spark is lack of a built-in file system like HDFS, which means it needs to be paired with Hadoop or other platforms for long-term data storage and management. Now, here is a more detailed comparison of Hadoop and Spark in a variety of specific areas. Architecture. The fundamental architectural difference between Hadoop and Spark relates to how data is organized for processing. In Hadoop, all the data is split into blocks that are replicated across the disk drives of the various servers in a cluster, with HDFS providing high levels of redundancy and fault tolerance. Hadoop applications can then be run as a single job or a directed acyclic graph DAG that contains multiple jobs. In Hadoop 1.0, a centralized job tracker service allocated MapReduce tasks across nodes that could run independently of each other, and a local task tracker service managed job execution by individual nodes. Starting in Hadoop 2.0, though, Job Tracker and Task Tracker were replaced with these components of Yarn. A resource manager daemon that functions as a global job scheduler and resource arbitrator. Node Manager, an agent that is installed on each cluster node to monitor resource usage. Application Master, a daemon created for each application that negotiates required resources from Resource Manager and works with node managers to execute processing tasks. And resource containers that hold, in an abstract way, the system resources assigned to different nodes and applications. In Spark, data is accessed from external storage repositories, which could be HDFS, a cloud object store like Amazon Simple Storage Service or various databases and other types of data stores. While most processing is done in memory, the platform can also spill data to disk storage and process it there when data sets are too large to fit into the available memory. Spark can run on clusters managed by Yarn, Mesos and Kubernetes or in a standalone mode. Similar to Hadoop, Spark's architecture has changed significantly from its original design. In early versions, Spark Core organized data into a resilient distributed dataset RDD, an in-memory data store that is distributed across the various nodes in a cluster. It also created DAGs to help in scheduling jobs for efficient processing. The RDD API is still supported. But starting with Spark 2.0, which was released in 2016, it was replaced as the recommended programming interface by the Dataset API. Like RDDs, datasets are distributed collections of data with strong typing features, but they include richer optimizations through Spark SQL to help boost performance. The updated architecture also includes data frames, which are datasets with named columns, making them similar in concept to relational database tables or data frames in R and Python applications. Structured streaming and mlib both utilize the dataset or data frame approach. Data processing capabilities. Hadoop and Spark are both distributed big data frameworks that can be used to process large volumes of data. Despite the expanded processing workloads enabled by Yarn, Hadoop is still oriented mainly to MapReduce, which is well suited for long-running batch jobs that do not have strict service-level agreements. Spark, on the other hand, can run batch workloads as an alternative to MapReduce and also provides higher-level APIs for several other processing use cases. In addition to the SQL, stream processing and machine learning modules, it includes a graphics API for graph processing and Spark or and PySpark interfaces for the R and Python programming languages. Performance. Hadoop processing with MapReduce tends to be slow and can be challenging to manage. Spark is often considerably faster for many kinds of batch processing. Proponents claim it can perform up to 100 times faster than an equivalent workload on Hadoop when processing batch jobs in memory. Although the performance gain likely will be much lower in most real-world applications. One big contributor to Spark's speed advantage is that it can do processing without having to write data back to disk storage as an interim step. But even Spark applications written to run on disk potentially can see 10 times faster performance than comparable MapReduce workloads on Hadoop, according to Spark's developers. Hadoop may have an advantage, though, when it comes to managing many longer-running workloads on the same cluster simultaneously. Running a lot of Spark applications at the same time can sometimes create memory issues that slow the performance of all the applications. Scalability. As a general principle, Hadoop systems can scale to accommodate larger data sets that are sporadically accessed because the data can be stored and processed more cost-effectively on disk drives versus memory. A yarn federation feature added in Hadoop 3.0, which was released in 2017, enables clusters to support tens of thousands of nodes or more by connecting multiple subclusters that have their own resource managers. The downside is that IT and big data teams may have to invest in more labor for on-premises implementations to provision new nodes and add them to a cluster. Also, with Hadoop, storage is collocated with compute resources on the cluster nodes, which can make it difficult for applications and users outside of the cluster to access the data. But some of these scalability issues can be automatically managed with Hadoop services in the cloud. One of Spark's main advantages is that storage and compute are separated, which can make it easy for applications and users to access the data from anywhere. Spark includes tools that can help users dynamically scale nodes up and down depending on workload requirements. It is also easier to automatically reallocate nodes at the end of a processing cycle in Spark. A scaling challenge with Spark applications is ensuring that workloads are separated across nodes independent of each other to reduce memory leakage. Security. Hadoop provides a higher level of security with less external overhead for long-term data retention. HDFS offers transparent, end-to-end data encryption with separate encryption zone directories and a built-in service for managing encryption keys. It also includes a permissions-based model to enforce access controls for files and directories. With the ability to create access control lists that can be used to implement role-based security and other types of rules for different users or groups. In addition, Hadoop can operate in a secure mode with Kerberos authentication for all services and users. It can also take advantage of associated tools like Apache Knox, a REST API gateway that provides authentication and proxy services to enforce security policies in Hadoop clusters. And Apache Ranger, a centralized security management framework for Hadoop environments. This combination of features provides a stronger security starting point compared to Spark. Spark has a more complex security model that supports different levels of security for different types of deployments. For example, it uses a shared secret authentication approach for remote procedure calls between Spark processes, with deployment-specific mechanisms to generate the secret passwords. In some cases, security protections are limited because all applications and daemons share the same secret, although that does not apply when Spark runs on Yarn or Kubernetes. The Spark model was primarily built to enforce security on top of data streams, which are less permanent than data stored for long periods. One concern is that this could open up Spark data infrastructures to a broader scope and scale of cybersecurity attacks. In addition, authentication and other security measures are not enabled by default in Spark. That said, sufficient protections can be achieved by combining the appropriate encryption architecture with proper key management policies. Machine learning. Looking at machine learning specifically, Hadoop is best suited as a staging tier for managing the extremely large data sets that applications often involve. It is good at ingesting raw data from various sources and storing the results of ETL processes for subsequent exploration and analysis by machine learning algorithms. In contrast, Spark is better for direct exploratory data analysis and deployment of machine learning models. Its mlib module includes algorithms optimized for various types of machine learning processes, such as classification, regression, clustering and pattern mining. The module also provides tools for feature engineering, pipeline development and model evaluation, plus linear algebra and statistics utilities. In addition, Spark is now the recommended back-end platform for Apache MapReduce, a machine learning and distributed linear algebra framework that initially was built on top of Hadoop MapReduce. However, Hadoop and Spark can be used together to support machine learning. For example, data scientists and data engineers may pull raw data from HDFS into Spark for interactive exploration and data wrangling. After the feature engineering and selection process is completed, the machine learning models will also directly aggregate and process data in Spark. Features that are interesting but not relevant for a specific project could be archived in a Hadoop cluster for potential future use. Deployment and processing costs. Organizations can deploy both the Hadoop and Spark frameworks using the free open source versions or commercial cloud services and on-premises offerings. However, the initial deployment costs are just one component of the overall cost of running the big data platforms. IT and data management teams also must include the resources and expertise required to securely provision, maintain and update the underlying infrastructure and big data architecture. One difference is that a Spark implementation typically will require more memory, which can increase costs when building out a cluster. Hadoop can also be a more cost-effective platform for running occasional reports on commodity hardware. And it can help keep costs down when organizations want to retain large volumes of data for future analytics projects. The broad Hadoop ecosystem includes a variety of optional supporting technologies to install, configure and maintain, including widely used tools like the Base Database and Hive Data Warehouse software. Many of them can be used with Spark, too. Commercial versions of the frameworks bundle sets of these components together, which can simplify deployments and may help keep overall costs down. Applications and use cases. Both Hadoop MapReduce and Spark are often used for batch processing jobs, such as ETL tasks to move data into a data lake or data warehouse. They both can also handle various big data analytics applications involving recent or historical data, such as customer analytics, predictive modeling, business forecasting, risk management and cyber threat intelligence. Spark is often a better choice for data streaming and real-time analytics use cases, such as fraud detection, predictive maintenance, stock trading, recommendation engines, targeted advertising and airfare and hotel pricing. It is also typically a better fit for ongoing data science initiatives, including graph computations and machine learning applications. Using Hadoop and Spark together. There are several instances where you would want to use the two tools together. Despite some asking if Spark will replace Hadoop entirely because of the former's processing power, they are meant to complement each other rather than compete. Below you can see a simplified version of Spark and Hadoop architecture. Organizations that need batch analysis and stream analysis for different services can see the benefit of using both tools. Hadoop can at a lower price deal with heavier operations while Spark processes the more numerous smaller jobs that need instantaneous turnaround. Yarn also makes archiving and analysis of archived data possible, whereas it is not with Apache Spark. Thus, Hadoop and Yarn in particular becomes a critical thread for tying together the real-time processing, machine learning and reiterated graph processing. Interview question and answer. Explain the key features of Spark. Apache Spark allows integrating with Hadoop. It has an interactive language shell, Scala, the language in which Spark is written. Spark consists of RDD's resilient distributed datasets, which can be cached across the computing nodes in a cluster. Apache Spark supports multiple analytic tools that are used for interactive query analysis, real-time analysis, and graph processing. Apache Spark supports stream processing in real time. Spark helps in achieving a very high processing speed of data, which it achieves by reducing the read or write operations to disk. Apache Spark codes can be reused for data streaming, running ad hoc queries, batch processing, etc. Spark is considered a better cost-efficient solution when compared to Hadoop. Name the commonly used Spark ecosystems. Spark SQL Shark for developers. Spark Streaming for processing live data streams. Graphics for generating and computing graphs. mLib machine learning algorithms. Spark to promote our programming in the Spark engine. What is graphics? Spark uses graphics for graph processing to build and transform interactive graphs. The graphics component enables programmers to reason about structured data at scale. What does mLib do? mLib is a scalable machine learning library provided by Spark. It aims at making machine learning easy and scalable with common learning algorithms and use cases like clustering, regression filtering, dimensional reduction, and the like. What is Spark SQL? Spark SQL, better known as Shark, is a novel module introduced in Spark to perform structured data processing. Through this module, Spark executes relational SQL queries on data. The core of this component supports an altogether different RDD called schema RDD, composed of row objects and schema objects defining the data type of each column in a row. It is similar to a table in relational databases. What file systems does Apache Spark support? Apache Spark is a powerful distributed data processing engine that processes data coming from multiple data sources. The file systems that Apache Spark supports are Hadoop Distributed File System, Local File System, Amazon S3, Base, Cassandra, etc. Name the types of cluster managers in Spark. The Spark framework supports three major types of cluster managers. Standalone. A basic cluster manager to set up a cluster. Apache Mesos. A generalized or commonly used cluster manager, running Hadoop, MapReduce and other applications. Yarn. A cluster manager responsible for resource management in Hadoop. Which languages can Spark be integrated with? Spark can be integrated with the following languages. Python, using the Spark Python API. R, using the R on Spark API. Java, using the Spark Java API. Scala, using the Spark Scala API. What are Spark datasets? Datasets are data structures in Spark added since Spark 1.6 that provide the JVM object benefits of RDDs, the ability to manipulate data with Lambda functions, alongside a Spark SQL optimized execution engine. What are the benefits of Spark over MapReduce? Due to the availability of in-memory processing, Spark implements data processing 10 to 100x faster than Hadoop MapReduce. MapReduce, on the other hand, makes use of persistent storage for any of the data processing tasks. Unlike Hadoop, Spark provides inbuilt libraries to perform multiple tasks using batch processing, steaming, machine learning, and interactive SQL queries. However, Hadoop only supports batch processing. Hadoop is highly disk dependent, whereas Spark promotes caching and in-memory data storage. Spark is capable of performing computations multiple times on the same dataset, which is called iterative computation. Whereas, there is no iterative computing implemented by Hadoop. What is speculative execution in Hadoop? If a node appears to be executing a task slower, the master node can redundantly execute another instance of the same task on another node. Then, the task which finishes first will be accepted and the other one is killed. This process is called speculative execution. Name the three modes in which Hadoop can run. The three modes in which Hadoop can run are as follows. Standalone local mode. This is the default mode if we do not configure anything. In this mode, all the components of Hadoop, such NameNode, DataNode, Resource Manager, and Node Manager, run as a single Java process. This uses the local file system. Pseudo-distributed mode. A single node Hadoop deployment is considered as running a Hadoop system in pseudo-distributed mode. In this mode, all the Hadoop services, including both the master and the slave services, were executed on a single compute node. Fully distributed mode. Hadoop deployments in which the Hadoop master and slave services run on separate nodes are stated as fully distributed mode. What are the main configuration parameters in a MapReduce program? The main configuration parameters which users need to specify in the MapReduce framework are: jobs input locations in the distributed file system, jobs output location in the distributed file system, the input format of data, the output format of data, class containing the map function, class containing the reduced function, jar file containing the mapper, reducer, and driver classes. What is the difference between an HDFS block and an input split? The HDFS block is the physical division of the data while the input split is the logical division of the data. HDFS divides data into blocks for storing the blocks together, whereas, for processing, MapReduce divides the data into the input split and assigns it to the mapper function. How does NameNode tackle DataNode failures? NameNode periodically receives a heartbeat signal from each of the data node in the cluster, which implies DataNode is functioning properly. A block report contains a list of all the blocks on a data node. If a data node fails to send a heartbeat message, after a specific period of time it is marked dead. The NameNode replicates the blocks of the dead node to another data node using the replicas created earlier. Thank you for watching this video. We provide hands-on training with labs, homework, group projects. Prepare you for the certification. Provide real projects. Internship opportunities. Support you and resume LinkedIn. Staffing support. Provide tech references. In-person online class. Class retake options and more. Call us at 847-350-9034 for your free career consultation meeting. Please do not forget to like, share, and subscribe to our channel for the latest videos.